Welcome, everyone. Today, we're jumping into a scientific detective story that seems to completely break the basic rules of math. It's a real mystery straight from the heart of the atom. So, let me just ask you this right off the bat. What if I told you that in some cases, 8 plus 8 is actually less than 16? I know, it sounds totally impossible, right? Like some kind of trick question. But it's actually the central clue in the case we're about to crack. You see, in the strange and fascinating world of atomic physics, this isn't a trick at all. The whole can literally be less than the sum of its parts. I want you to imagine building something with Legos, and when you're done, the final creation weighs less than all the individual bricks you started with. That's the exact puzzle we're looking at today. Now, every good investigation needs a specific case, a subject. And our case today is all about a very common and stable atom, one we all know, oxygen-16. And every detective needs evidence, right? Well, here's ours. Our main clue, pretty much all the data we're going to need, comes directly from this single page of a physics textbook. You can think of this as our official case file. It has all the numbers we need to solve the mystery. Okay, first things first, let's break down our subject. What is an oxygen-16 nucleus actually made of? It's pretty simple. 8 protons and 8 neutrons. 8 plus 8. These are the fundamental building blocks we need to account for. All right, time to pull out the calculators and do some math. We're now starting the calculation phase of our investigation, our search for the defect. This is where we hunt for the precise amount of mass that seems to have just vanished. And what's really cool is how simple our investigation plan is. We're going to calculate the total mass of the protons, then the total mass of the neutrons, add them up to see what the total should be, and then compare that number to the atom's actual, real-world measured mass. Let's do it. Step 1. The protons. So our textbook page tells us that a single proton has a mass of 1.00728 atomic mass units, or AMUs for short. We multiply that by 8, and we get our first number, 8.05824 AMU. Next up, the neutrons. Now, a single neutron is just a tiny bit heavier, clocking in at 1.00867 AMU. 8 of those gives us a total mass of 8.06936 AMU. Okay, here's the big moment. Let's add our two piles of bricks, the protons and the neutrons, together. Our expected total, the mass we should get for the oxygen-16 nucleus, is 16.1276 atomic mass units. Remember that number. But here's the twist. This is where it gets weird. When scientists actually put an oxygen-16 nucleus on the scale, they don't get our number. The actual measured mass is only 15.79491 AMU. There's a very clear difference. Something is definitely missing. So, exactly how much is missing? Well, a quick subtraction gives us the answer. 0.33269 atomic mass units have just seemingly disappeared. This is our missing mass. In physics, they call it the mass defect. So, we've found it. We've measured the missing piece. But the biggest question of all still remains. Where did it go? And to solve that, we have to turn to the most famous name in all of physics, and, well, Einstein's famous equation. This is it. This is the question that completely changed our understanding of the universe. If the law of conservation of mass says mass can't just be destroyed, then where did it go? The answer is right here, hidden in these 5 elegant little characters. E equals mc squared. It's probably the most famous equation in all of history, and it is the key that solves our entire case. And here's the mind-blowing part. The mass wasn't lost at all. It was converted. Einstein's incredible insight was that mass and energy are really just 2 different forms of the same thing. That tiny bit of missing mass transformed into a huge burst of energy when those protons and neutrons all came together to form the nucleus. And just how much energy are we talking about here? I mean, it's a tiny sliver of mass. But using the conversion factor from our textbook, that tiny amount of mass unleashed an incredible 309.7 mega electron volts of energy. Trust me, on an atomic scale, that is an absolutely colossal amount. Okay, so we found the missing mass, and we found out it became energy. But so what? Why does this energy even matter? Well, finding it is one thing. But understanding just how important it is, that's everything. This energy actually has a name. It's called nuclear binding energy. And you can think of it like this. It's the cosmic superglue that holds the center of the atom together. It's the force that's strong enough to overcome the fact that all those positively charged protons should be pushing each other apart. It locks the whole thing down. And this isn't just some abstract idea from a physics book. This binding energy literally shapes our entire reality. It's the reason atoms are stable and don't just fly apart. It's the engine that powers our sun and every single star in the sky through nuclear fusion. And, yep, it's the exact same principle that we've harnessed here on Earth for all nuclear power. So, we've solved it. The case of the missing mass is closed. It didn't vanish. It became the very energy that binds our universe together. But that solution leaves us with one final, incredible question to chew on. If you can turn mass so powerfully into energy, could you do it the other way around? Can you turn pure energy back into mass?